All right, guys, so we just took a look at another important technique of circuit analysis, namely that of source transformations. Keep in mind that sometimes there are circuits that you can use source transformations in order to simplify. However, not every circuit itself is going to lend itself to source transformations in order to simplify the circuit before you analyze it fully. One thing that we still have left pending, which is what we're going to do right now, is I want to go through an example of a circuit that can be analyzed quite effectively through the use of source transformations. And you'll see that even analyzing a relatively small circuit does lead to a great number of source transformations. And one of the things that you'll also see is that even though it is pictorially intensive, at no point are you going to be setting up a system of equations as you do with the generalized techniques of circuit analysis, like the node voltage method or the mesh current method. This is one of the major advantages of this type of transformation. So with that said, let's get into the example. So this is on source transformations. And this is an example. Now, just a quick reminder of what a source transformation is. So suppose that you happen to have a voltage source that happens to be in series with a resistor R here. So let's call this Vs, I'll call this Rs, and let's say that this is the point A and B. You can actually replace this system with another equivalent one with respect to the terminals A and B, rather than it being a voltage source that happens to be in series with a resistor. You can actually replace it with a current source, not in series with a resistor, but in parallel with a resistor, like this. So suppose that this is Rp, this is I sub P, provided two things are true. So these will be equivalent if, first and foremost, Rs and Rp, they must have the same value. And the second thing is the relationship between the voltage source and the current source in each one of the circuits looks like Ohm's law, but keep in mind that it is not Ohm's law, right? So it's Ohm law-like, but it's not the same thing, because the voltage source and the current source are belonging to completely different circuits. So the fact that the voltage source belongs to one circuit and the current source belongs to the other makes sure, guarantees that it's not Ohm's law, but it's close to it. Now, the example that I have, that we're going to go through fully, the prompt is the following. I want to find the power associated with the 6-volt source. So we're looking for the power that's either being generated or dissipated by a 6-volt source, and the circuit's the following. Immediately on the left-hand side of the circuit, we have our 6-volt source, and it is connected to a large number of resistors here, a network. So we have resistors quite literally all over the place. There's even one down here. There's one last resistor. And then on the opposite end of the circuit, we have one last voltage source. This is a 40-volt source. And then the circuit is complete. Now, the value of these resistors are such that this is 4 ohms, this is 6 ohms, this is 30 ohms, this is 10 ohms, this is 20 ohms, and lastly, this is 5 ohms here. Now, the strategy, really, before we even get started, the strategy is going to be the following. I want to begin on the right-hand side of the circuit, and through a series of source transforms, as well as a few equivalent circuits with resistors, I want to reduce the entire circuit to one that looks somewhat like this. So through source transformations, we wish to reduce the above circuit to one that looks like this. One where we have the 6-volt source here. There's one equivalent resistor there, right? And if we can do that, we can then calculate the current that's flowing through the circuit, and then the power associated with the 6-volt source is the voltage times the current. So here, but it really all hinges on being able to find that equivalent resistance. So let's go ahead and start taking a look at this. And if you actually take a look at the circuit that we have above, notice that if I were to isolate this terminal and that terminal there, like this, and I take a look at what's on the right-hand side over here, right? Notice that what I actually have there, well, I have a voltage source that happens to be in series with a resistor, which means I can turn it into a current source in parallel with the same resistor. Keep in mind that the rest of the circuit there is actually going to come along for the ride. So one of the things that I want to do is I'm going to actually perform the source transformation, but the rest of the circuit I'm actually going to keep the same. So notice that I've kind of copied and pasted everything that, oh, I cut it. I didn't copy and paste it, I cut it. So let's put that back. Oh, look at that, beautiful. Okay, so, but with respect to the terminals A and B, let's get rid of this. What I'm going to do is I'm going to replace that voltage source and resistor that are in series with one that is parallel with a current source. Now keep in mind, and this is going to be something that's important, the details in electrical engineering matter. Notice that here the voltage polarity that we have here, and this is important, is such that the top here is positive, the bottom is negative. This will immediately for us dictate the direction of the current in the source that we're replacing it with, right? So over here, notice that I have no choice but to say that the current is going up this way, right? On top of that, notice that the value of this resistor and the value of the resistor up here, they're the same value. Question is, what should the value of the current be in the current source? Well, that's given to you through this relationship. So here, I can say that Vs is equal to R times I sub P, or I sub P is Vs divided by R. Vs was a 40-volt source, R was a 5-ohm resistor. So I sub P should be 40 over 5, that is 8 amps. That means that this is 8 amps. Now, notice that one of the nice things about this, right, is that we now, in the new circuit, this resistor and this resistor are now in parallel with respect to one another, which means we can add them in parallel, right? So let's go ahead and do that. So if I take the 20 ohm resistor, add it in parallel with a 5 ohm resistor, That's 20 times 5 divided by 20 plus 5. On top we have 100 ohms squared. On the bottom we have 25 ohms, which if you calculate out gives you a total of 4 ohms. So I can actually replace that entire section here, this resistor and that resistor, with one equivalent one with 4 ohms. Right. So let's actually do that. Just like before, I'm going to take this right here. I'm going to copy it. I'm going to go ahead and paste it down here. Let's move it into place like this. So this resistor that we had right there with respect to the terminals A and B is now being replaced by a 4 ohm resistor. And the current source over here now is a current source that is providing us with a current of 8 amps. Whoops. Like this. Right. Now, you might wonder, well, why is it that this is an improvement? Well, it's an improvement in the sense that the circuit contains less elements than it did previously. And if you take a look once again, notice that if I isolate some new terminals here, suppose that I call this terminal C and D, what I actually have here to the right of that is I have a resistor that happens to be in parallel with a current source. Right? And according to my source transformations, well, what can I actually replace that with? I can replace that with the same resistor that is now in series with the voltage source. So once again, this section that I have over here with respect to the new terminal C and D, I can actually perform a source transformation on this. So if I isolate the terminal C and D like this, that resistor that was in parallel is going to be the same resistor that's in series. My voltage source is going to have this particular polarity, and the value of this voltage source, well, it has to be the resistor times the current source. That was a 4 ohm resistor. This is an 8 amp current source. 4 times 8 is 32 volts, so this is now a 32 volt source. And the rest of the circuit actually comes along for the ride. So let's actually see if I can carefully cut out and duplicate this portion of the circuit. And what I now want to do is I want to paste it there, and let's clean this up a little bit. So we had 6 ohm resistor, 4 ohm resistor. Down here we had a 10 ohm resistor like this. And this is the new circuit that we're actually left with respect to the terminals C and D that were right there. Now, if you take a look at this new circuit, we have quite a number of elements that are in series with respect to one another. There's this resistor, this voltage source, and this resistor. I can combine all 3 of the resistors because they are in series into one equivalent resistor. So here, what I'm going to do is I'm going to keep this portion of the circuit. Let's copy this. Let's paste it right below like this. Now, here I have one resistor that is now in series with my voltage source. My voltage source I can keep where it was. But here, this resistor has the equivalent resistance of the 6 ohm, the 4 ohm, and the 10 ohm, all in series. Notice that if you add up those numbers, you get a 20 ohm resistor, like this. Right? As you can see, this has actually improved quite a bit. Right? We're further along in our goal using the source transformations in order to solve a problem. Now, I'm sure you can guess by now, this circuit lends itself to multiple source transformations. And if you take a look at that terminal and that terminal, what you see to the right of this terminal, we have a resistor in series with a voltage source. You can source transform this as well. So I'll call this terminal E and F. And I'll use a source transformation here. Which means that with respect to the terminals E and F, I am replacing the series resistor with a parallel one, the voltage source with the current source. The current must go up. The value of the resistor must be the 20 ohm value. And the current of the source, well, it's the voltage of the source divided by the resistance. This was a 32 volt source. This was a 20 ohm resistor. I should be able to calculate this without a calculator, but let's verify on my calculator anyway. This is a 1.6 amp current source. And then on the opposite side of the circuit, you have the same circuit that you had previously. So this is still the 4 ohm resistor, the 6 volt source, and then the 30 ohm resistor. I'm sure, again, you can see the game that we're playing. Notice that we have these two resistors there. They're in parallel with respect to one another. We can add them in parallel. So let's actually do that. So here, 30 ohms added in parallel with 20. That's 30 times 20 divided by 30 plus 20. And let me get my calculator to calculate this. So 30 times 20 divided by 50. This gives us, oh, this is a nice number. It's 12 ohms. So here, the above circuit, I can replace that one equivalent resistor. So this is a 4 ohm resistor. Here, I added those two in parallel, so this is now a 12 ohm resistor. This is in parallel with a 1.6 amp source, like so. And let's, for good measure, play the game one last time. So if I isolate these two terminals, I had E and F, let's call this E and H. Notice that what we actually have is we have a resistor in parallel with a current source. So this itself, once again, lends itself to a source transformation. So here, if I isolate my terminals G and H, on the right-hand side, I have a resistor. It's a 12 ohm resistor in series with a voltage source. We also have a 4 ohm resistor here, a 6 volts, whoops, let's not put that in the inside. How about we put the polarity in the inside? Our 6 volt source, like so, and we're almost done. The value of this voltage source, well, it should be the current source times the resistance. This has a value of 1.6 amps times 12 ohms. And if I use my calculator to calculate that, so 1.6 times 12, that's 19.2 volts, like this. All right, so this is a 19.2 volt source. And one thing that you should be able to see is that this and this are in series with respect to one another. On top of that, this voltage source and this voltage source, they essentially have opposite polarities, right? So the entire system you can actually replace with one voltage source whose polarity looks something like this. One way in which you can kind of picture this is if you were to take this voltage source and you were to move it over here, notice that the negative terminals on this one would be touching the negative terminals on that one, and the one that has the larger voltage is actually going to end up winning. So the voltage source value that we actually have here is going to be the 19.2 volts minus the 6 volts for a grand total of 13.2 volts. And the equivalent resistance of the last resistor that's actually left here, well, it's the 4 ohm resistor plus the 12 ohm resistor in series. This is 16 ohms. Now, the reason this is important is because, again, notice that there's actually going to be a current that flows through this circuit, right? And the current itself is going to flow through the 16 ohm resistor, and we can actually calculate what that current happens to be. And notice that the current itself is flowing in that direction. So here, that current, say I equivalent, right, well, it's got to be the 13.2 volts provided by the voltage source divided by the 16 ohm resistor. And if you calculate this out, I can't do that in my head. I have the suspicion that very few people can. It's 0.825 amps, right? Now, let's take inventory. Let's go back to the original problem that we had. Notice that what we actually wanted to do was we needed to figure out what this current was that was flowing through the circuit in order to calculate the voltage or calculate the power that was associated with that source. Right? So here, the power that we actually have that's associated with the 6-volt source, because we now know the current that flows through it, well, it's this equivalent current times the voltage that this provides us with. And this is 0.825 amps times the 6 volts. And if you actually calculate that out, so 0.825 times 6 volts, this is a grand total of 4.95 watts. Also keep in mind that we did end up employing the passive sign convention on this, right? On top of that, notice that this right here also tells us that the power itself is actually being absorbed by the 6-volt source, not dissipated. And this was what we were looking for.